Okay, so the first speaker of today is Shie Mannor. He's a professor of electrical engineering at Technion. And he earned a PhD in EE at the Technion in 2002. And he was then a Fulbright postdoctoral associate at the MIT for 2 years. He was subsequently a professor at McGill University for 6 years, where he was an incumbent of the Canada Research Chair in Machine Learning. Since 2009, he has been at the Department of EE at Technion, where he is a full prof. He has published more than 70 journal papers, 130 conference papers, and he got 8 patents. His research awards include several Best Paper Awards, the Henry Taub Prize for Academic Excellence, an ERC Starting Grant, an HP Faculty Award, and a Murray Fellowship. Shie's research interests include machine learning and data science, planning and control, analysis and control of large-scale systems, and interconnected systems. And I want to say on a personal note that on top of that, he's a good friend. So Shie today is going to speak about adaptive label acquisition in non-stationary environment.
All right, thank you. Can you hear me? So I'm going to talk today about work that I have been doing with Walmart Labs at Walmart Global Ecommerce. Just to give you an idea, Walmart is the 4th largest e-commerce company on the planet, and of course the largest company at the planet in general in terms of sales. And they have a lot of data. So more data than you can imagine, actually. So I'm going to talk about some e-commerce problems that are perhaps a little bit out of date. They're all supervised learning problems. And this is just to give you some examples of the kind of problem that they have to deal with. So one of the issues that they have is that products are being onboarded. So a new reseller brings them a catalog of maybe 500,000 new products. And the number of products that you can buy at Walmart.com is about, it's more than 20 million products. So they get about 1 million new products every month. And some products are retired, of course. And then they need to decide how to classify them into taxonomies. So they have, for example, a product type. What is a shoe? What is a lace? What is a TV? So they have to classify products that they get. They have to extract attributes from products, color, brand, other attributes. It may not be as easy as it sounds because sometimes the description of the product is quite in text or in an image. And also they need to do things to which you might more be familiar with, like estimate the click-through rate, add to cart, rates. This is the probability that the product is going to be eventually purchased, and many other many other problems. So they have lots of supervised learning problems. If we look at the product as the main marker here, so they have said think about getting 1 million products every month. There is no way you can even look at this number. Like you cannot even hire people that work in India or China that will do it for you. I mean, the issue here is mostly that they know how to build machine learning algorithm, but they need to be able to evaluate them quickly, and they need labels. So labels are expensive, and you should think about that. I mean, if they're on board 1 million products a month, they can maybe label 2,000. That's by the way, labeling sometimes requires expertise, so you cannot offload it to someone who doesn't know much, or you cannot use Mechanical Turk easily. And then, so the question is really, how do you use the labels that you have in a good way? So let me make this into a mathematical formulation. So this is a supervised learning setup. There are n items. that we need to evaluate. Every item, we call it xi, and the labels are y. Think about n as a very large number, essentially infinity for all practical purposes. We can generate models. So for example, we can look at the probability that of a label y given the item x. Item can be textual description, images, and so forth. And theta is going to be the parameterized model. So in this talk, we're only going to talk about model-based learning. If you wish, you can think about it as a logistic regression model, but there are many other models would work here. So basically, I mean, what you'd like to have is you will eventually choose the argmax as your hypothesis. So this is going to be the maximum posteriori, whatever you prefer it, and L is going to be a loss function. And the goal is to estimate the risk, and this is really the risk, the empirical risk estimate, the classical one. You go over all the items, and then you look at the integral of the loss over the label. So this is sort of the classical risk estimator, and of course we want high accuracy given the budget of labels that we have. So collecting labels is expensive for this estimate, and the main issue here is that we cannot hope to have here all our n items, but rather a very small number of items. So you can think about it, I'm going to be able to sample only a fraction of the items that I want to. Here is a simple approach, sample n random items. You have a budget of n, so this is how many, say, hours you can take of the labelers, and then you estimate the risks based on your sample. But that sounds pretty easy, and we can normalize it efficiently if you wish. But then there is a problem with a USB as well. There are several problems, and one of the problems is that items change over time. So items are born and items die. So you think about just, I mean, nobody's going to buy a 33-inch TV, right? At this point in time, I mean, maybe 5 years ago, this would have been a great hit, or 10 years ago. And then you need to do evaluation over multiple subsets. So it can be the case that somebody is going to tell you, I just want to look at electronics, or I just want to look at items that are above $100, or I just want to look at items that are blue. So you need to do evaluation over multiple subsets and over multiple risk measures as well. And then the issue that if you already managed to get a label, the question is how do you use it? So I labeled an item as a black Samsung 67-inch TV 3 months ago. Now somebody asked me a different question. I still want to reuse my label. The question is how do I do it efficiently? And if you'll just do a simple estimation, what you'll see is that you don't use the model, or if you have a most likely model that you kind of believe at the moment, you're just not going to ignore it. So your estimate is going to be the same for all your parameterization. And that seems wasteful and also wrong. All right, took some time. So is that the slowest snack around? So next speakers, just wait. So let me give you a motivating example here. So I have here 1 million items. As I said, this is what you'll get in a month in terms of throughput. I built a classifier. Doesn't really matter how I built it. And now I can sample n items, and I have an editor who's usually a highly trained individual. So think about it as someone who has a master's or a PhD degree in English Lit, or something like that. And I'm going to do now, I need to have this evaluation block. So my evaluation block take my classifier, which is built God knows how, and the true labels over a small subset of the items, and it's supposed to give me a risk estimate. So, I mean, the easiest thing to do would be to say, well, just sample uniformly at random, everything is going to be fine. And that's okay. I mean, you can do it, but the question is, what will happen as time goes along and you get more items coming in, items coming out, different budgets. So for example, you might have a budget of 500 examinations or labels, or then a job budget of 1,000 labels, and your range of items changes. So let's continue with the example. Here I want to compute the risk over 1 million items. I have 1,000 labels. So it's pretty simple, right? I'm going to sample 1,000 items, then I'm going to get 1,000 labels. I'm going to measure the risk, just the empirical mean of my errors. Pretty simple, right? So let's see what can go wrong with that. All right, so now somebody tells me I'm going to add 500 items. 500,000 items, sorry. And then I'll ask you to compute the risk on all 1.5 million items. All right, so let's suppose for now that I want to use the previous risk measure. So I'm happy with the previous risk measure of classification error for now. And then it could happen that this is not, the 500K are different than the 1 million, and it could be that the products makes changes, but let's ignore that for now. So those are issues, let's ignore them. So here is one thing you can do. I can sample 500 items from the 1.5 million items. I can compute the risk on the new 500 labels that I have over all 1.5 million. And then I can ignore what I saw before. So essentially I wasted 1,000 labels that I had to work very hard and pay a lot of money to earn. So what you see here is that the blue is what I'm going to use now for my estimates, the blue curve. Okay, but here's another approach. I get an extra budget. I'm going to sample the 500 items from the new items alone. So only from the new item that I got here, I'm going to sample. And now I'm going to compute everything based on 1.5K labels. So instead of using 500 labels before, I use 1,500 labels now. So I have much more information with this approach, and I don't waste any label. Okay, so but what happens now if I have only 250 labels? So this is the budget that I get. So how should I sample? So I claim that you can show that it's best in a formulation, in a way that will make precise, to sample those 250 items only from the new items. And then you need to account for the difference in sampling. So basically you'll have 1 over 1,500, sum over all the old items plus 2 times the new items. So this is sort of going to be like an important sampling type of correction. I'm correcting now for what I've seen before. All right, so at this point you can say, well, this looks pretty easy, but let me ask you a question. So what happens now if I have, say, another 1,500 samples? What should I do? Anyone cares to guess? All right, so think about it. But as you can see, the problem will become complicated very quickly. So what are the challenges here? So the challenges are that whenever you want to sample new test labels, I mean, just sampling, if I give you a few more samples and you ask you, give me a risk estimate, sampling from scratch does not make any sense. It's prohibitive. Whenever if you want, I'll give you a new risk measure. So before we'll just look at classification loss, but it makes sense to look at, say, weighted classification loss or other measures, and this will also be very wasteful. So the point that I'm making is that knowing how the previous labels were sampled is something that you need to do. So you need to know how you sampled beforehand to sample the current item in the best way and to compute your risk estimators. And that's what we're going to do in this talk. So in this talk, we're going to propose a general approach for optimally sampling new items. And over time, as it can become very tricky to reuse labels, because the sources of label change, because the distribution of the items change, because items die, because new items are added, so things can become complicated. Let me just illustrate it with an example. So here, this is just an example. So we started with 1,000 items, so we sampled them, say, uniformly, and then we got another item, so we sampled them like that. And then we got some more samples, and now we weren't sure what to do, but somebody gave us some labels for free. Those things happen. And then we get a more additional, those are the green samples here, so we sampled some more, but we also get, for some reason, we got some free items, and then we got the purple, and weren't sure what to do, so we had some more labels, and we sort of filled it in. And then somebody gave us those weird, this black sample, so we even have more labels. And as you can see, you can get very quickly a cubist image here, right? Like the probability of sampling any item here can become very quickly very complicated, and indeed it does. So, and you should expect that because a catalog of items is something that is very much alive, and it changes very rapidly. So this is just to show that things can get tricky, and we have actual real graphs that I'm not allowed to show you that are much more complicated. So the number of color there goes to essentially the number of months that Walmart exists. So you can get complications that are tens of different levels of sampling. So what's our agenda for the talk? So we'll propose a new estimator for risk. It's going to be related to some things that I'm sure you've seen, but as far as we know, this is new. We're going to show you how to minimize the estimate of the variance for a given budget. So if you give me some budget, I'm going to tell you how to sample optimally. And then we'll show you that, in fact, you can use your current belief on the best parameter. So if you know the parameter, or you can sort of bootstrap your estimate to reduce variance further. And then I'm just going to briefly mention a few examples. So at this point, we're going to embark on the discussion on trying to solve this problem. Are there any questions at this point? So I know it's morning, so they told me to be entertaining. So let's tell you that this is really all about risk. And I'm taking a huge risk now because my wife is in Paris with my credit card. But other than that, let's move on. Okay. So what's the idea then? So for every item that we have, we're going to keep a probability PI. This is a probability of sampling this item. Whether or not we sample it, we'll still keep this probability forever. So if we have 20 million items, like we do, then we'll have to have 20 million numbers. That represents, those numbers represent the probability of those items having been sampled. Maybe they have been sampled and we have their labels, maybe they haven't. We don't know. But we keep those probabilities at a safe place. And then we define the risk estimate. So our risk estimate, this is going to be what's known as a self-concurrent risk estimate. That's, this is a normalizing factor. Zi, a Bernoulli random variable with probability pi. That's probability of sampling. So we look at the sum of Zi over pi, and this is the normalizer. And those are the sum of Zi over pi over all item of the loss. So if we have here Zi equals 0, then this is just 0 times something. And if we have Zi equals 1, it means that this item has been sampled. So we have a value there that we know. And we can assume that the labels are correct. So if this is the case, we'll essentially always require that the sum of pi equals b. That's going to be the expected number of labels that we required. So our process stops being a deterministic process. Somebody gives me a budget B, and I'll tell them, look, I'll try to do my best, but I'm not going to have exactly B. I'm going to have a random variable whose mean is B, and whose variance is quite small. So they shouldn't be too upset if I don't manage to get to B, but I'm a little bit more than that. So that's a risk estimator, and essentially from now on what we'll do in this talk is we'll discuss the properties of this risk estimator. One thing you need to notice is that we need to always, for things to be well defined, we need all the PJs, all those probability to be positive, to be non-zero. That's something we'll have to take care of. And then if your PI equals PJ for all I and j, then this is just a standard estimator, right? It's basically a standard estimator. There is nothing new here. And you can show that this estimate is consistent, and in fact, you can even prove exponential bounds on the convergence. I think Nicola already probably did it in his head. So you can prove it's consistent. It's not very different than the usual one. And it's related to important sampling, and I'll talk more about it later, but this is not important sampling. As you'll see, there is a delicate algorithmic difference and also an interesting statistical difference. All right. So once we have an estimator, being an aspiring statistician, what I'm trying to do is I'm trying to minimize the variance of this estimator. So just look at this is the expression that I really want to minimize. WI is the Bernoulli random variable over PI. LI is the losses. And once you see this term, you can fairly quickly convince yourself that you can approximate the variance if the PIs are not very large with the term that we see here. So it's 1 over n squared, sum over all item, 1 over PI minus 1. So this is essentially the probability that or the expectation of an exponential variable, but that's beside the point, time the expectation of the loss minus the true risk that you're trying to estimate. So moving from here to here is an exercise in algebra and some optimistic estimations or things you don't need to pay attention to. And there's nothing really complicated here, but there is an interesting message. So what PI should I have in order to reduce this term? So here I have a multiplication. If my loss is large, I want the term here to be small. So if this term here is to be small, then PI has to be large, right? So my goal here is essentially to make this product small. So if the expected loss is large, then the probability of sampling should also be large, intuitively at least. And if the loss here is, for example, 0, then I don't care. PI can be very, very small. So the intuition that you get from this estimate is to minimize variance, I would like to sample more where my loss is large. But how do I know that my loss is large? If I knew my loss, I'm done, right? There is no need to solve this problem. If I had R and I know that this is large, then the problem is fairly easy. So we'll address this issue. But this is sort of the analysis here that I want you to bear in mind. And as I said, this approximation holds. In fact, there is some asymptotic normality here. They told me it's machine learning in the real world, so I decided not to write any theorems to appease the crowd. So let's look at what kind of an expression you get here. So if I'll give you a budget B, then basically you can look at this risk estimate, and it turned out that you're looking for the sampling profile for the PI that minimizes what you see here. So this is minimized sum over all item. This is a term you don't know, but let's suppose for now you know, for the sake of discussion, over PI. And subject to sum of PI equals B, and PI, of course, is between 0 to 1. So if this is the case, then this is a fairly easy problem to solve, so it turns, from an optimization perspective. Because at least if all the losses are the same, then you can solve it with bisection. And if the budget is small enough, you can show that the analytical solution approximates what's written here. So you take a fraction of the budget and you normalize according to the standard deviation of the loss. And this is just a normalizer. And this problem is easier to solve. It turns out that you can do a bisection on the dual variable. The math turns out to be correct. So you can solve this problem exactly. Of course, if you know the risk, which would mean then that you don't need to solve it. All right, so this is the problem that we want to solve. But then the question is, how do you handle not knowing the risk? So the answer is the following. Well, there is no real magic bullet here, but there are at least some things you can do. If the model is a black box, for example, you can take this to be a constant over all I, and you have a current estimate, so you can solve it. In that case, PI turns out to be uniform, which is pretty, I think, well expected. But if it's not black box, for example, if somebody tells me all TVs go hand in hand, all shirts go hand in hand together, they have a similar loss, then I can do a lot more. I can do grouping, I can do clustering, I can do many things. And indeed, this is what much of the work is about. Much of the work is about sort of clustering this expectation of the loss to groups, and then moving on to solving the problem. Okay. Let's suppose that now I have existing labels. So already some of the labels exist, but somebody gives me an extra budget of B. So now I want to be able to use the existing labels in an optimal way. So I have a new budget, B overline. And I want to, it turns out that the problem is fairly similar. Now it's just minimize over PI overline of the terms here. So it's essentially the same thing. I just need to have a correction here. And note that when I do sampling, there is no need to do replacement, because I don't replace anything. Once I have a label, I keep it. I don't want to ask for the same label twice. That's the whole exercise here. So we get another optimization problem, which is not very far from what we saw before. Remember that the PIs are something I don't need to optimize. Those are just constant at this point, as far as I'm concerned. So this is essentially just a linear version of the previous problems, and I can solve it in the same way. Okay. Again, it turns out that while seemingly this does not look like a convex problem, in fact, you can solve it easily using a bisection on the dual variable. The dual here is very convenient, by the way, because essentially the dual becomes a single variable that you really care about, and you do bisection over it, and everything is fine. And the way you should think about it is what you get from this problem is what some people would call water filling algorithm. So what do we mean by water filling algorithm? You have a budget here. That's a sample that I used to have before in red. We assume here constant expected square loss for the sake of discussion. So you give me budget in blue, and then basically it's like flooding water into the probability space. I'm going to make sure that I have enough, whatever budget you give me, I try to push the smallest PI to be as large as possible. So this is why we call it water filling. And if it'll give me enough budget, then all the P's are going to be the same. All the new probabilities are going to be the same. So the less I know about an item. For example, here initially I don't know anything. After I just got the red labels, I don't know anything. But now that I get the blue, I basically I sample it with the highest probability possible. And then with enough budget, eventually I'll get uniform sampling. So the moral here is that if you'll give me enough budget, I'll always get something uniform, but you'll never give me enough budget in practice. So I'll often going to get things that look like this. And that's sort of the intuition here, that I'm going to get water filling. By the way, anyone cares to guess what happens when I don't have a constant, or let's suppose I have two groups of expectation of Li minus R square? Anyone cares to guess? There will be two water fillings with two different levels. So there will be level for group 1, level for group 2, and now I'm going to essentially equate them in total, so their contribution to the risk is going to be the same. So in some sense, it's water filling over water filling. So it's water filling per group and water filling overall between the groups. So that's nice. By the way, how am I doing on time? Okay. So let's see here a synthetic example that we generated. So we had 1,000 labels from uniformly collected from 100,000 items. And then we added 50K items with a new budget B overline. And the risk of the initial items is small, and the risk of the new items is large. And we asked the question, how much, what's going to be your risk error as a function of the budget? This is standard error. So, I mean, the scales here do not matter. All you need to know that they're 20%, 40%, and this is normalized to 1. So once you do the optimal sampling, I mean, you see that essentially you get a lift for the small budget size of roughly factor of 2. And then eventually everything will converge optimally because everything is consistent here, right? Eventually they're all going to get to an error of 0, and all of them are asymptotically normal. It's just that the rate of getting to asymptotic normality is very different between those items. So this is just to give you an idea. The blue is the optimal sampling, the green is the uniform sampling, and the red, striped red, is the existing plus uniform over all sampling, over all samples. So just to show you that it can work. And now let's, what happens when risk is weighted by items? So what we can show is that basically in terms of variance reduction, we can optimize, we can optimally use our budget by reusing all labels that we've seen ever. And the only overhead that we really have here is to solve an optimization problem, which I told you is essentially a convex optimization problem, or it's convex after a small conversion, a small trick, and you need to keep PIs. So if it's worth for you to keep, say, 20 million probabilities, then this is something you should consider. All right, so what happens when you have a model estimate? So here the question is, before we said that we can look at the expected square loss. If we have groups, we can estimate it. But what happens if we don't have groups? So here we can do something which is akin to bootstrapping. So we can substitute R with the loss that had no parameter of the model with the loss given that we believe our model is correct. So if somebody tells me, look, your parameter theta is close to optimality, or it is optimal, then what should you do? So we can replace our risk with modified risks that depend on my model parameters. And we can substitute the conditional probability of label given X with the conditional probability of label given X and model, which the model is not correct. It's not a true model, but this is my best estimate so far. And you can bootstrap and everything is still going to work and you can prove that it works. And for 0-1 loss, things actually happen to be very, very simple. So for 0-1 loss, which is not the loss that Walmart cares about, by the way, because it's not rich enough. But for this particular loss, you can show that you get a very simple expression. So basically, this is a thing is sort of a standard trick in machine learning, so I'm not going to. But this is you can make it pretty. It opens up pretty simply. And then the main issue that you get here, what you'll see if you develop it, that you're going to sample on certain labels much more frequently. So basically, you'll sample the labels you're less sure about more frequently because you have here 2 parts, and that's exactly what we had before. This is something you cannot do anything about, but the label that you care most about are going to be the one with large uncertainty here. All right, so let me give you another example. This is something that people have been looking at when they do transfer learning. So in transfer learning, you have 2 data sets. You have one which is, let's say, completely open to you. So you have labels and data points, and one which is less known to you. So you need to actively sample labels from this point. So here we see the email example. So this is estimation error, absolute estimation error, and this is a labeling, how many labels you sampled. This is some example from that people have been using, and here we see the passive example, passive sampling, so basically sampling in random, and here we see active sampling where we actually use a model. This is for some classification as spam, no spam problem. We actually use a model that we think is the best one. So you see that there is a boost, a significant boost here when you're doing something active. All right, I want to take one or 2 minutes to just tell you what's a connection to important sampling. So this all seems related to importance sampling, but in importance sampling, you actually need to do something different. You need to have this probability distribution of sampling, and you need to maintain it per item. So you need to have this sum I equals 1 to n. You need to summarize to 1, and then you sample items with replacement, and then you use the importance sampling estimator instead of the self-concurrent estimator that we have been using. So you can say that this seems like a very similar problem, but it's not. And the reason is that that at least I was unable to, and my colleagues as well, to incorporate existing labels into importance sampling. So we don't know how to do it efficiently, how to do it. Maybe you guys know, but we haven't been able to do that. So importance sampling is also a variance minimizing estimator, but it's not, or at least we don't know how to make it appropriate for the situation where you get labels incrementally. And also, can be pretty tough to manage the PIs because you need to have them always normalized to 1, where in the approach that we presented here, the PIs do not need to normalize to 1. You just keep them. You just have it in your pocket, and all they need to do is to be between 0 and 1. All right. So let me summarize. So if with a very small cost of just storage and optimizing, you can better leverage all the data that you have. This has been a key for the success in estimating risk measures in a fairly complex real-world problem. In particular interest here is what happens when your data are changing over time, when the subsets, when the distribution of the data are changing. And of course, when some of the data points that existed before do not longer exist or are no longer relevant. This is something that is applicable to many supervised learning problems, many risks. And in some sense, I would say this is a dual of active learning. So this is some of the problem that you have all the items, you keep the probabilities, but you're asking for labels only on a need to do so because somebody else gives you a model to evaluate. And finally, there is a much benefit on the way you can sample if you know what will arrive. So if somebody tells me that some items are going to arrive, I can probably do some things like dynamic programming and probably do a lot better. At least from our experience, this is not the case. Nobody knows what's going to arrive. But if this is the case for your problems, then you can probably benefit a lot by that. And with that, I'll conclude. Thank you for your time. Yes.
Sorry, just wanted to try and make sure I was on top of a few things there. When you had the B overbar budget and then you sampled, that was the sort of new denominator there is the new value. You've updated the probabilities with that,
exactly.
That new value, right?
Exactly.
Okay. And the other thing I wanted to just check was, you said that when you have this estimate of you don't know whether it's good or not, but you use it to sort of drive your sampling methodology. Do you have some way of sort of figuring out whether it was good post hoc? I mean, you know, you're sort of believing in it a priori and you're saying, okay, I'm going to use it. Is there some way of sort of, you know, at the end of the day, patting yourself on the back and saying, yeah, no, it was good and I actually did benefit this much from that?
So that's a good question. The short answer is no, because we're already using all the labels that we have. Eventually, we can acquire at cost additional labels and do that, but essentially you cannot do it because you're already doing a variance minimization procedure. And in fact, at least for logistic models, you can show that you're going also information. I mean, if you believe a logistic model, or L1 regularized logistic even, what you're doing is optimal in terms of information as well. So if you can compute the information again and redo this whole talk from, if you'll invite me to an information theory in the real world conference, then you can redo everything and you get the same thing.
Okay. Thank you.
I have a question about how you use it in practice on real data, and specifically in how do you use the fact that maybe points that have been labeled years ago are not relevant, and the distribution somehow change. Do you have this problem in practice, or you just...
So every, at least for the, say, the taxonomy problem, which is making sure that every item is labeled in the right location in the product tree. So knowing that, say, a shoe is a running shoe, an ASICS running shoe, and so there we don't have this problem because if something becomes stale, it's not in the product tree anymore. What does happen is that sometimes you can have a vendor that would dump 500,000 products that are all different types of nails. So and then you need to readjust for that, and that's something that people are doing on a higher level. So they have a higher level of essentially reducing the importance of some groups.
Thank you.
Still have a bit time.
In your talk, you mentioned the labels which were always right, right? You don't handle the probability of a label being,
yes.
being wrong. You have, I assume for Walmart it's always the case, but you've not tried to...
So we have tried working with a Mechanical Turk, and we have used a similar approach. Essentially, it still does work. The problem is that for some tasks, the Turks are not good enough. And for some tasks, they are, by the way. But for the product classification, they're just not good enough. It's too complicated for someone who earns, $50 for an hour or something to do it mindfully. But we have tried with Mechanical Turk for some problems, some other problems, and for that you can make the relevant corrections, and it would still work. It's the model itself still holds.
Last question. Well, I do have one actually. So when you're in your talk, when you describe how you're going to do samples the second time, so you have this first bunch of labels, and you're going to you have an extra budget. You say, okay, I'm going to solve this problem, and it seems like it's the optimal probability just depends on the past probabilities and not on the realized events. Is that correct, or?
No, that's not correct. So whenever you sample something, then you know it has been sampled.
Yeah.
So your probabilities, PIs, you're not going to sample the same item again in our model because we assume that the labels are correct, that are redeeming assumption. However, the way it works is that you have this vector of PIs, yep. This very large vector, 20 million long vector, and then you update it with the optimization problem. You sample, you update it with a new batch comes, and so forth and so forth. So in fact, we have something like more than 2 years of batches, and there are many batches, approximately once every 2 weeks. So what you get is something that is fairly varied at this point in time, and it does depend on the realizations of what happens, because that's sort of something that might happen, might have importance.
It makes sense, but I missed it during on the mathematical formulation that you displayed. I saw that.
Okay.
Thanks. So, is there any more questions, or no? Well, I can thanks Shie again.
Thank you.